Hello everyone, I'm Monika Bhushan and today we are starting lecture number 15 of linear algebra. In today's class we are going to see a very conceptual topic which is eigenvalue and eigenvector. So before starting to calculate eigenvalue and eigenvector, we will first understand the concept of eigenvalue and eigenvector, and then we will be seeing that where we have to use eigenvalue and eigenvector, that means why we have to study it. Fine, we will first understand the concept behind eigenvalue and eigenvector. Okay, that means what is the reason that we have to study it, where we see the day-to-day life application of eigenvalue and eigenvector. Okay, and then we will see the mathematical terms of eigenvalue and eigenvector. Okay, so let us assume that we have taken some picture. Okay, or maybe we have taken our selfie. Okay, so when you see your selfie, you identify it that this is you. Fine, no? So what are some of the key information, okay, that you use to recognize it that this is you only? So let us elaborate little bit. A selfie will have some elements such as nose, eye, etc. Fine. So your overall selfie, that is overall data, can be seen as matrix, and this matrix has some key information, that is the dimension, principal component, which we might call as specific features like nose, eyes, etc. So these principal components or these principal dimensions can be seen as eigenvectors, okay, with each one of them having their own elements. Okay, so we can say that eigenvectors and eigenvalues are the information stored in the matrix. So eigenvalues and eigenvectors are used to reduce the complexity of data, or more precisely reduce the dimensionality of data, but it retains most of the original information. That means when I see my selfie, most of the information are stored in eigenvectors and eigenvalues, and more or less they are responsible to make us identify our picture. So finding eigenvalues and eigenvectors of a matrix can be useful in those areas wherever we are in need of transforming a large volume of multidimensional data into smaller dimensions. But eigenvalues and eigenvectors retain most of the information. Okay, so we can say that the primary goal of eigenvalue or eigenvector is what? To achieve optimal computational efficiency. Okay, fine. So how do we define eigenvalue and eigenvector? So here it is written that eigenvalues and eigenvectors of a square matrix. That means we have to work on n cross n matrix. Fine. So the definition says that given a square matrix A, if there exists a scalar lambda, okay, it can be real number or it can be complex number, and a non-zero column matrix X, fine, such that Ax equals lambda x, then lambda is called an eigenvalue of A and x is eigenvector of A corresponding to an eigenvalue lambda. Okay, so what does it mean? So the definition says us that suppose we have taken one matrix A. Okay, this is some square matrix A. Okay, so this is some arbitrary square matrix. X is a vector, that means it has dimension also, it has some magnitude also. Fine. We know that vector is also a matrix. Fine. No? Either this is 1 cross n or this is n cross 1. That means vector is a matrix that can have just one row or just one column. So all the rules that work for matrices also work for vectors. Here is the example of some square matrix. Fine. This is 2 cross 2 matrix. Okay, and this is the example of row matrix. Okay, or you can say that this is the example of column matrix. Fine, no, but they both are vector also. Fine. So this X can be called as matrix also. Okay, so as per definition, if we are multiplying this square matrix A by a vector which is represented by matrix X, okay, then if the direction of this resultant matrix remains same as of vector X with some scaling constant, then we will be saying that this X is nothing but the eigenvector. Why this is eigenvector? Because if I am multiplying this eigenvector by this square matrix A, then the resultant matrix is also having the same direction as of vector x. Here we are considering that x is non-zero vector. Fine, no? Because any matrix multiplied by zero vector will give another zero vector. So in that case, this scalar multiple or this lambda will become trivial. Here we call lambda as eigenvalue. Eigenvectors cannot be zero vector, but there is no restriction with the eigenvalue. Eigenvalue can be zero, but eigenvector cannot be zero. So if we will understand the same thing with some graphical representation, this is some two-dimensional graph, and here this is some vector x. This vector has some magnitude and it has some direction also, okay? And if I am multiplying any square matrix by this vector x, and if the direction of this resultant matrix, okay, this is the resultant matrix, if the direction of this resultant matrix is not same as of the direction of x, then we will say that x is not eigenvector. Okay, if we will see some other scenario, here again we have some two-dimensional graph, and then this is the vector x. This vector has some magnitude and it has some direction, okay? And if we have multiplied this square matrix by this vector x, then the resultant matrix, which is ax, is actually having the same direction with some scaling factor lambda. Then we will be saying that this x is eigenvector. Okay, and this scaling factor can be in opposite direction also. So we can have the resultant matrix in opposite direction also. This is also okay. What we have discussed, when any square matrix multiplied by any vector results in another vector in the same direction or opposite direction by a magnitude of some scalar quantity which is lambda, then the vector is called the eigenvector of that matrix. I know. And since the direction is not retained in this resultant matrix, so here we say that x is not eigenvector. So this was the concept behind eigenvalues and eigenvectors. Now we will see that how to calculate eigenvalues and eigenvectors. Okay, as we have seen, this is your ax equals lambda x, fine, where a is square matrix, x is eigenvector, and lambda is eigenvalue, and here x is again eigenvector. Okay, so we can write it as ax minus lambda x equals 0. Fine, we can write in this way. Okay, but be sure that this 0 is not a scalar. This is what? This is a zero vector. Right now, this is the zero vector. So this equation 1 we can write in this form also. We have taken out x. So this is what? A minus lambda. Now this is I. Okay, this I is what? This I is identity matrix. Okay, this is identity matrix. And I hope you know what is identity matrix. We have covered these all things in lecture number 1 only. So why we are multiplying I here? Multiplying by identity matrix is just like multiplying by 1 for scalar equations. Here we have vector. So in other words, we can say that multiplication of this I does not affect the values in this equation. Fine, no. What is identity matrix of order 2? That means for 2 cross 2 matrix, this is the identity matrix. If you are multiplying this matrix, then it will not have any effect in the values of this equation. Fine. Now, to make this equation true, what we have to do? We have said that x is not a zero vector. Fine, no? X is not a zero vector. This condition will become true when A minus lambda I is singular matrix. Fine, no? And what is singular matrix, identity matrix? We have already discussed. Fine. Or in other words, we can say that determinant of this A minus lambda I should be equal to 0. Fine. This is the singular matrix. This is my equation number 2. Okay. So this equation is called as characteristic equation. And the roots of this characteristic equation will be called as eigenvalues. So to find the eigenvalues, we had to get the roots of this characteristic equation. And this only we are going to see using the example. Fine. So if you find this class useful, please like and subscribe my channel. Thank you.